So the next speaker is Chen, also known as Mark. So he's currently working towards the PhD degree in civil engineering and computer science at Stanford University, and he's being advised by Professor Rajagopal. His research focuses on energy resource control, convex optimization, data privacy, and their applications with machine learning. So a very interesting topic. Chen, the floor is yours.
Oh, hi, everyone. Can you guys hear me?
Yes, we can. Yes, we can.
Okay.
We are not seeing you, but we are hearing you.
Oh, sorry. How about here?
Okay, much better now.
Okay. Let me share the screen. Hold on.
Okay, great.
Okay, hi. Should I start?
Sure.
Okay. Hi, everyone. This is Xiao. Also, feel free to call me Mark. This is a joint work together with Thomas and Rajagopal from Stanford University. And today I'm going to talking about the energy resource control via privacy preserving data. So here's the outline for today's talk. First, I'm going to introduce the motivation and also related work and potentially our contribution, followed by the architecture of the method. In particular, I'm going to focusing on the storage control as one of the example, and then introducing the min-max training, which is largely inspired by the GAN framework, and also introduce the following two examples. One is from the synthetic data set, and the other one is from the real user data set from the Irish pilot demand response programming. So the motivation is very simple for the problem, because in practice, the distributed energy resource lies under the ownership of the, sorry, maybe I should minimize this, the ownership of the many users. But however, the distributed energy resource operation requires a lot of data that can contains a lot of sensitive information. For example, it is possible to infer some like household income or square footage of your house from the meter data. So a service provider such as the utility company or or the distributed energy resource aggregator, they will need a privacy measures for the owners to exchange their required data. Or in other words, before these data users to upload their data to the cloud service, some third party might need to consider to incorporate some privacy manipulation or protection to release the data for the downstreaming tasks. So there are a bunch of related work already kind of like covers the relative related topics like the data manipulation, including the pre-processing aggregation and noise injection. So the pre-processing probably may not remove the correlation between the sensitive labels like income and the data. Even the data itself has been altered a little bit. And also the aggregation to achieve the privacy may excessively alter the utility of the data itself. It can be the situation that the data will change quite a lot after this aggregation. On the other hand, the differential privacy, which has already been discussed in a previous couple of talks, has already shown a very good potential. It involves noise injection to achieve a strict notion of the privacy. But the differential privacy usually cannot be too strict, and sometimes it can be excessively alter the utility of the data. And finally, the user demand shaping is another approach which achieves the privacy by physically alter the data source through some device operation. For example, like incorporating the storage to basically smoothing out the raw trajectory of the power consumption. However, it requires a balance between the device utility and privacy, and it limits by the device constraints. So in our work, we pretty much present a methodology for data privatization using the noise injection, which can be considered as a variant of a differential privacy, but however, they're slightly different. We incorporate a very lightweight linear filter for the privatization to occur in a local device level. And we try to balance the privacy and data utility and try to investigate the trade-off between them. In our context here, the privacy definition is pretty much the correlation or the classification accuracy of the private attributes. And the adversary classifier here is trained on the predicted private attributes. And then the classification accuracy is related to the mutual information between the private attributes and the metadata. On the other hand, the utility definition in our context is the performance of the storage control using the privatized data. In specific, the performance here is measured by the cost. And the use case is a storage control for the cost minimization. So here's the high level for the scheme of our architecture. The idea is very simple. By just looking at the picture, we feed in the raw data and then pass that through a linear filter as well as a privatized label together with a random noise. And then we spit out a privatized data. And the whole idea is that the privatized data has a lower correlation with the sensitive attribute like income or square footage of your house compared with the raw metadata. And we use we both minimize the energy cost and maximize the adversary loss. So here's just a warm up like problem formulation for the traditional storage control problem. Here in the objective, we have like the energy cost, which D here stands for the original raw demand. And the X in and X out stands for the charging in and out control variables. And all the remaining like L2 penalties are just showing you want to minimize the battery operating cost in the sense that you don't want to charge and discharge too frequently. And here the constraints is pretty straightforward as well. So it pretty much follows the dynamic of the batteries. The next time step states of the battery equals the previous time step plus and minus the discharge amount and plus in the charging amount. And eta here is the efficiency. And followed by some like capacity of the battery. And the next slide is just converting the original. The first equation is just converting the original deterministic case into the stochastic case where the demand here is sampled from a data distribution. And here I simplified the feasible set to consolidate them, represent them through a capital X. And again, the adversary loss here adopts the cross entropy loss, which is very simple. And phi here is a very simple neural network. So again, here's one of the core part of the minimax training, which is the first part is the utility loss, where we pretty much want to minimize the energy cost for the control. And the second part, second term of the minimax training here is we want to here maximize the adversary loss, where the adversary loss is minimized through this cross entropy. And the constraint here is we generate the privatized demand through the linear filter G here, which basically product with the random noise concatenated with ground truth variable, ground truth label Y, and then add them to the raw demand. So one of the issue here is that because now the control cost is minimized by the privatized demand. So how different the control decision could be comparing with the control that optimized with the raw demand, that's a very interesting question that we're going to cover in the next few slides. So before I dive into the experiments, the methods are potentially applicable in the real world setting, where basically the linear filter is trained offline through a min-max optimization using anonymous batches of the privatized data. And then the learned weights are passed on to the data owner. The data owner uses filter weights to calculate the noise injection and privatize their own data locally. And finally, the privatized data is sent to the DER operator for the use of control optimization. Then let's briefly introduce the case studies. The first case study is the home demand data with the solar generation aggregated under secondary transformer. The goal here is using the storage to minimize the energy cost for a group of homes located under the secondary transformer. The utility here again is a cost saving compared with the optimal control. And the privacy here is classifying high or low income homes. So here I show the two plots. The upper panel shows the raw demand, which the blue color shows the high income homes, and the red curve shows the low income homes. So before privatization, the raw data trace can be seen that it's clearly separates from high income and low income. But after the privatization, the two kind of like categories of homes smeared together, and it's kind of like becoming harder to distinguish which trajectory comes from high or low income. So on the right-hand side, this is the plot showing the different trade-off between the privacy and the utility. So the utility here is measured by the gap between the raw control cost minus the privatized demand control cost minus the raw control cost divided by the raw control. So we can see that as we put more and more weights on the privacy, the original loss of performance loss for the control cost is still very minimal, only get 5 to up to like 8% loss, performance loss, versus the accuracy here drops dramatically from almost like 89% down to 72%. And then for the second case study, we investigate the real data set, which is from the Irish customer behavior trail. The goal here is we use again the storage to minimize the energy control cost for individual homes. And the utility here is a cost saving compared with the optimal control, and the privacy is again the classification of the square footage of your house. And here I transfer the square footage into the large or small homes. Again, this is the plot showing the trade-off between the privacy and utility. When we put more and more weights to the privacy, the accuracy classification accuracy drops down from the 75% to the 50%, almost like the random guess 50-50, and then the performance loss doesn't deteriorate too much from 8% to like say 10 to 12% maximum loss. And then we also test on the different training and test split of the data. And we see the performance is pretty consistent with the slightly change when we have a smaller training data set. The accuracy kind of like goes up a little bit, but overall it's pretty robust. Again, so we also implement our method in a current deep learning framework in a PyTorch in specific, and we compare with kind of like the state-of-art optimization solver like a Groby and a Mosaic, and we observe that our in-batch parallelization can pretty much match up with the state-of-art convex solver. So in the end, this is conclusion. We first introduce a method that to provide privatize the data through noise injection that balance the trade-off between the privacy and utility in this context of storage control. And we also observe that the noise injection through the simple linear filter is very, very lightweighted, and it can be run on the local device after training. And there are some limitations for the current version, which that the training requires solving an optimal control problem in the loop, which can be computationally expensive when we scale it up to many devices. So we're still working, looking into the training issue and how to speed the min-max optimization up to a very large scale. So after that, that's pretty much it.
Okay, thank you, Xiao, for the nice presentation. So we have 5 minutes left, 4 minutes to be precise. So I will open for questions, and we have a question from the audience. So Rahul Gupta says, thanks for the presentation. And then he has, I think, three sub-questions. He asks, the battery power is modeled by charge and discharging variables. How do you make sure that both are not non-zero at the same time? So maybe you ask that first, and then we go for the two.
Oh, sure. Yeah, very good question. So in this context, we are not necessarily caring too much about whether they're simultaneously non-zero, because in the end you are able to summing them up and just to get the net value out of that. But in particular in this case formulation, because we add by the way, do you guys can see my screen?
Yes, we can.
We added this L2 norm penalization, and from our observation, there are very rare cases that both X in and X out are non-zero. Either one of them is zero in the majority of cases.
Okay, thank you, Xiao. The other two questions are how the hyperperimeter beta are tuned, and how can you please comment on its impact on the performance? And the other one that you can also reply.
Oh yeah, sure.
Is for CMU to run? You can also reply to the next one, which is for CMU running comparison. Green bar represents solution using gradient descent approach. This is, I think, a simple question. Okay.
Oh yeah, sure. I'll answer the last one and go back to the second one. The last one, the CPU comparison, yes. This one, yes, they are running based on the stochastic gradient descent, yes. And for the second one, oh, I see. The beta here, let me click this. The beta here, you can think of this as like how strong you want to enforce the frequency of charging and discharging. So if a beta is large, super large, then the X norm will be very close to 0, which means that there won't be any power to charge or discharge for the battery. So in this context, we put a beta in a small value, like I believe 0.001, something like that. The scale is very small, just to give a tiny bit incentive for the battery to not frequently charging the discharge, to oscillate it too frequently.
Okay, thank you, Xiao. So I think that's it. We have no other questions, and we are. It's 5 o'clock. Oh yes, of course, Terence. Go ahead. A short one.
Yeah. What are actually the theoretical guarantees on privacy?
Oh, for this context, you mean the theoretical guarantee means sort of like the differential privacy guarantee?
Actually, or just let's say I'm the consumer and I'm just asking, so what are my guarantees by using your mechanism?
So the privacy here is basically decorrelated the private attributes from the raw meter trajectory. So in the sense that if you pass the privacy mechanism, there's some like sort of a certificate, a small certificate that doesn't necessarily give you the differential privacy guarantee, but tell you like your original correlation is reduced a lot, and how much quantity has been reduced depending on the parameter choice of your trade-off between the utility and privacy.
Okay, yeah, thank you.
Does that, yeah, okay.
Answer my questions, yep.
Okay,
cool.
Everyone, so I would like to thank the authors a lot. So thank you, Xiao, thank you, Kate, King, Lucas, Terence, and Theodoros. It was a very interesting session, and I would also like to thank Federico, who has been hosting the session, and of course thank the participants, because we had many of them. So we were more than 30 most of the time. So their questions were also very interesting and very important. So thank you all. I think it was a very good session, and hope to see you soon. Bye bye.
Thank you. Bye, guys.
Bye bye.
Bye.